So this one is the second session on vector algebra. Last session just we revised the two definitions which are our most important definition for vector calculus, and that was dot product and the cross product of the given two vectors. Okay, so these are very important definitions actually. Remember these definitions we are going to use in each and every example of vector calculus. Okay, that is in the next topic. Okay, now we are moving to here triple and quadruple products. So given a three vectors, we can multiply them. Given a four vectors, yes, we can multiply them. So we have the formulas for that known as the triple and quadruple products. Yes, these formulas we not require in vector calculus. They are limited to here only. So just yes, few of the triple product formulas, yes, we require at some places, but not about quadruple, definitely. So suppose we are given this three vector A, B, and C. Okay, the vector A, B, and C. Now we can multiply again in a two different ways here. Whenever we multiply like this, A dot B cross C, A dot B cross C, it actually gives us the volume of a parallelepiped whose coterminous edges are these vector ABC. Now what is the coterminous edges? That these three vectors are terminating at the same point, or we can say their starting points are same. So if you see the vector A bar is here, this is the vector B bar, and this is the vector C bar. So if you have three coterminous edges of a parallelepiped as a ABC, then the volume of that box, the volume of that parallelepiped, okay, the volume of this solid is given by this A dot B cross C. So it is denoted by, the notation is like you say box product of, this is the square bracket ABC. So when we write a square bracket ABC, it is actually the box product A dot B cross C, A dot B cross C, and it is given by a determinant again. Okay, so yes, obviously this is a scalar product. The resultant quantity is a scalar quantity because when we evaluate this 3 by 3 determinant, we get some number. So first row is obviously the component of this vector A bar, second row is the component of a B bar, and third row is a component of vector C bar. So that about the definition for a scalar triple product or the box product. Now, whatever the properties we have for the box product here, all these properties are nothing but they are the properties of determinant. Okay, so these determinant properties, if you know the determinant properties, you can easily write the properties of the box product here. Can anyone tell me what happens in determinant when any two rows are identical?
Zero.
The
So
zero.
determinant becomes zero.
Very good. So whenever any two rows of a determinant are identical, the value of that determinant is a zero, and because of this if you observe here, one of the properties written, if you observe this box product of CCB is 0. That means if one of the vector repeats in the box product, the value of that box product is a 0 because the property of determinant. By chance, suppose one of the property comes in the exam to prove, then yes, you should know that proof is just by the property of determinant. You just write box product of CCB is equal to 0 is equal to determinant, like you can write the component of C bar as a C1, C2, C3, and again C1, C2, C3, and B1, B2, B3. You can say as two rows of a determinant are identical, that value of determinant is 0. So the box product should be 0. So that way you can write the proof within, if it comes, it will come only for 2 marks, not more than that. So just go through the proofs if you want. The proofs are there in the book again. If we interchange any two rows of determinant, then value of determinant
will remain same.
not correct.
Sir, negative. Sir, negative comes up.
Negative.
Yes, I told
Negative.
only two rows. If we interchange any two rows, then the value of determinant changes in a sign only. So because of that, we have this property. Here is a property. If you observe, if we change the position of any two vectors only two vectors, we replace interchange A, B position, because of that minus sign appeared outside the box product. Minus sign appeared outside the box product there. And if we interchange all the three rows of a determinant, then value of a determinant Yes,
Same, sir, same.
remains same. Yeah, correct. So when we interchange all the three rows of a determinant, then value of determinant remains same, and that gives us this property. Here is that property. If you observe, ABC is replaced by BCA, BCA is replaced by CAB, we can say there is a cyclic change in ABC. So obviously, if we interchange all the three positions, then the value of box product or scalar triple product remains same there. So this is again by the property of determinant. So these two proofs are by property of determinant. There is one more simple result is here, that box product of the unit vector ijk is 1. The box product of unit vector ijk is 1. This question is asked in one of the exam to prove that box product of ijk is 1. So remember, the proof is of one line only. If we start with the box product of ijk, by definition, box product of this ijk will be, yes, it is a determinant. Yes, anyone? What should be the first row?
1 1 1.
I1, I2, I3.
1 0 0, because the component of component of vector I are 1 0 0, because okay, and the component of j are 0 1 0,
0 1 0
and this
0
is
0
0
1.
0 1.
0.
So this is the A B C. These three vectors are just ijk given. So by definition of a box product of ijk is this determinant, and if you evaluate this determinant, you get it as 1. So that's the proof.
Excuse me, sir.
Yes.
Sir, we know that like triple product is if a triple product of ABC is like A dot B cross C, so we can write it I dot J cross K. J cross K is I only, so I dot I
Yes,
is
that
1.
way
We can
also you
write that
can
also.
prove it. Yeah, correct. Okay. Yeah, some proofs are there are multiple ways, and if you are logically correct, yes, definitely you are correct there. So yes, if you write it is I dot J cross K, and J cross K is I again, and I dot I is 1, and that is another way of writing the proof of this. And you see, the proof will come for 2 marks. You can do it any of the way, both way. That is a correct. Okay, if it comes there, I'm saying. Now, another property says this dot and cross are interchangeable. Means when we write A dot B cross C, we can say it is equal to A cross B dot C. So this is also true. So dot and cross we can interchange. Now another property says here this box product represents actually the volume of that parallelepiped we already seen. So whenever we are given that ABC are the coterminous edges of a parallelepiped, then the volume of that parallelepiped is of this box product ABC. Not only that, we can find the volume of tetrahedron whose coterminous edges are ABC. Now let me say this is our tetrahedron. So this is the A vector, B, and this is C. So these are coterminous edges ABC. Now if we join this, sorry. So this is one of the side of the tetrahedron. This is the another side of tetrahedron. Sorry, this is the base of tetrahedron, A to B, and there is one more side that I draw by another color so that you can identify. So this is C to A. So indirectly tetrahedron is like this. So base is triangular there. All surfaces are triangular there, like this. Okay, that is a tetrahedron. So I may not good in that drawing here. I hope all you are getting this tetrahedron. Okay, like this. Clear? So tetrahedron is a solid whose all surfaces are triangle there. So it is bounded by 4 triangles, I will say. So the volume of a tetrahedron whose coterminous edges are ABC, that is 1/6 of box ABC. So indirectly we can say in one parallelepiped there are 6 tetrahedron. We can fit 6 tetrahedron there. Okay. Any doubt in these properties?
No, sir.
Okay. Now the last property is a distributive property. You can say at the bottom. This property is again by the property of a determinant. Can anyone tell me one similar property you learned for a determinant? What is that property? There is a property for determinant.
If a row or a column is in the sum, then we can divide it into the two determinants.
Yes, very good. That you are correct. Okay, if any row or any column is a sum of the two elements, then that determinant can be expressed as a sum of the two determinants there. Okay, so this is the same property is used here, and we get the property for the box product. So in determinant you learned like this. I will write it here. So I will take a simple determinant so that you will get it clear idea. So I'll say x1 plus y1 a, x2 plus y2 b. So if this is determinant you have, so this determinant, this first column is a sum of the two entries. So what we can do it, we can write this as a sum of two determinants. And the first determinant is obviously x1, x2. This is the first entry is here, a, b, and then y1, y2, and again a, b. So value of determinant remains same. So this determinant is expressed as a sum of the two determinant. Okay, so this is the property that you learned in determinant. That exactly same property is here now for the box product. So what is property that you should remember? If any of the vector is a sum of or a sum or the subtraction of the two vectors, yes, you can expand that box product as a sum of the two box products there. So obviously here the middle term is a b plus c. So this b plus c gives us a b d. That is first box product is a b d and the second box product of a c d there. So that is one of the result here written. Not only that, sometimes not a single vector as a sum of two terms. Here the middle term is a b plus c, the last term is d minus e. Now yes, you can apply this distributive property to each and every term one by one, and you can come to this answer here. For example, you get a b d, then a b you will get with a minus e, a b minus e, then a c d and a c minus e. But whatever that minus e is there, that minus sign is taken outside, and you can write it in single step also. In a single step also, just you have to write it one by one if you are not getting this directly. Okay, any doubt in the distributive property?
No, sir.
Okay, so good. So there are many properties here for scalar triple product only. For remaining products like vector triple product or quadruple products, there are no properties. Okay, just it is the formula is there that we have. So I will come to the next set of the definitions here, the definitions of remaining vector triple product. Now three vectors multiplied so that the resultant quantity is a vector again. Okay, here the resultant quantity is a vector. So you'll observe A cross B cross C. So A cross B cross C. So that is the obviously A cross B is one vector, and cross C is again a when you take cross product you get a vector quantity. Now there are two ways to evaluate this cross product. Yes, one of the way you can calculate A cross B separately by our determinant method. Then you take cross C. Okay, but in few of the proofs you cannot ABC not given and certain things we have to prove it there. So that time these results are important that you have to remember. So A cross B cross C is equal to A dot C into B minus B dot C into A. Now here hint is given to remember. The hint is this one. You can remember this as 1, 2, 3. A, B, C as 1, 2, 3. So 123 is equal to 132 minus 231. Okay, you can remember like this. 123 is 132 minus 231. Okay, like this. So yes, A cross B cross C is equal to A cross C. Sorry, A dot C into B minus B dot C into A, that way. Okay, B dot C into A. So that way you can remember. So this is the hint just to remember. There's nothing with this of this with the formula. But remember, this cross product is not commutative. We already know that A cross B is not equal to B cross A, or A cross B is not A cross B is equal to minus of B cross A actually, and because of they are not equal. Similarly, this cross product is not associative. This is not associative also. You can say A cross B, A cross of B cross C is not equal to A cross B of cross C. So you'll observe the bracket position is only changed. Whenever we change the position of the bracket, then the cross products not remain same. They are not equal. They are again not equal, not commutative, not associative also. And because of this, you should remember one more formula for the left right bracket here. So when we have A cross B cross C, now here the bracket is for the first two vectors, here the bracket is for the last two vectors. So in such a case, you should remember this the formula 123 changes to 132 minus 132 minus 123 itself. 132 minus 123 itself. So that's about a vector triple product. Any doubt in the definition? Because it's just definition. Actually, it's said that A cross B cross C can be calculated by this formula also. There is no alternative to by heart this formula. You should remember the formula to get a quick solution for triple products there. In the similar way, last part that we have is a quadruple product. So this is a vector product of 4 vectors now. So we can multiply 4 vectors so that the resultant quantity is a scalar quantity. So we can take A cross B separately. We can calculate C cross D separately, and then you can take dot product of them. Yes, you get that answer. You can get that answer. Remember, these 3 definition, whatever we have, vector triple product, scalar quadruple product, or vector quadruple product, if you not remember, then also you can do the calculation, but that calculation becomes lengthy. And another way, in some proofs, you have to require these formulas, and because of that, you should remember it. Otherwise, examples you can do it without these formulas also. So what it says, A cross B dot C cross D is a determinant. This is a determinant of A dot C, A dot D, B dot C, and B dot D. So these are the entries of that determinant there. So that's about scalar product of 4 vectors or scalar quadruple product. Scalar quadruple product. So product of 4 vectors. And last is vector quadruple product. Product of 4 vectors in a resultant quantity is a vector again. So A cross B cross C cross D. Now this quadruple product you can treat like a triple product also. For example, this AB are as it is there. So these ABs are as it is, that are considered as 1 and 2. Instead of C, we can take C cross D as 3. C cross D as a 3. So you can observe 123 is 132 minus 231. Same formula we used here. This is the same formula there. 132 minus 231. So it is 132 now in this case. It is a box product of 1, 2 and 1, 3, 1, 1 and 3 and then into 2. So 1 and 3 means box product of ACD. Box product of ACD into B minus 2, 3, that is a box product of BCD into A. So that way again you can remember. So yeah, I'm just giving you the hint to remember these formulas. Remember, just like we use this formula for getting quadruple product, we use this formula and we get this result. This is the result. Yes, we can apply this formula also and we can get this result. Okay, for that, yes, obviously you have to treat that AB as 1 and CD as 2 and 3. So here 1, 2, 3 like this, and now you'll get this formula. By this formula you get another result. So either you write ACD into B minus BCD into A, or ABC into ABD into C minus ABC into D there. Okay. Any doubt in the formulas?
No, sir.
Okay, very good then. Now only the examples left now. So these are the 4 definitions that we have. Out of that, box product is mainly we require in calculus later on. Other these definitions not required there. So the question number the first question is here, that one is asked in 2008. We are given 3 vector ABC and the question is find the vector A cross B cross C. Now, there are obviously 2 ways. One of the way is a lengthy way. Yes, you can calculate A cross B first, then you can calculate A cross B cross C. That is also the correct and you get the same answer. Instead, we can use here the definition that we see right now only. So let me start a solution here. A cross B cross C. Now this is a 1, 2, 3. Which formula that we have? 132 minus 231 or 132 minus 123?
So 132 minus 231.
Minus 231. Okay,
Yes, sir.
check. So 132 means 13, that is A dot C
A dot C B.
into B minus B dot C into A. So this is just for our understanding in exam. Yes, you can write it in rough or you can strike out that later on because it is nothing with the original example. Okay, so don't keep as it is that in the exam. So examiner may think what you are done, what you done there. Okay, so like that. Yes, it is just for your understanding the formula or to recall the formula, that is the hint there. Now the problem becomes simple here because we have the vector ABC. So we are taking A dot C. Let me calculate A dot C. A dot C. So that is A1 B1. So you'll observe 1 into 1 is 1. Then A2 B2, that is minus 1, plus A3 B3, minus 1 is a plus 1 into B bar as it is. So we are taken A dot C there. A dot C minus, now we are calculating B dot C. So 1 into 1, that is 1, minus 1 into minus 1, plus 1, and lastly plus 1 into minus 1 is a minus 1. So that is B dot C into A. Is that clear? So obviously we left with B bar minus A bar only. And now just you have to do a subtraction. Subtract A bar from B bar. So we have to do the subtraction of these two. So I minus I, that is a 0 I. Then here you will have minus j is a minus 2j. And the last k plus k, that is a 2k. So minus 2i plus, sorry, minus 2j plus 2k is the answer. Any doubt here?
No, sir.
So if you finish, tell me so that we can take the next question then.
Yes, sir.
Yes, sir.
So I will move to the next question then. So here is the second question. Even though question number 3 is written, so that's the second question here that we have. Determine a lambda so that these three vectors are coplanar. What should be a condition?
Sir,
Scalar
their
triple
box
product
product
is
Sir,
is
you have
0.
to
zero.
Equal to
divide it.
0.
Correct. So one of the
Yes, sir.
property of the box product is there that volume of the box is 0. Then the given three vectors are coplanar. They lies in the same plane. That points lies in the same plane, or that position vectors lies in the same plane. So simply we have to start with the box product is equal to 0. Question was asked in 2011. Remember in recent 3-4 years, we don't have any question coming on this topic. So generally the topic is considered for 0 marks there. But one of the paper, I think box product of Isaac equal to 1, that show that that question was asked only. Okay, come to the point here. So we have here as the vectors are coplanar, we can say the box product of this vector A, B, C is 0. The box product is nothing but it's a determinant. The first row is 1, 1, 1. Second row is a 2, 0, minus 4. And third row is 1 lambda 3. Now just we have to evaluate this determinant and we get that lambda is equal to 5 by 3 as answer. So let me see how to expand. So write it 1. Let me expand along the first row. 1 into its minor. So 1 into this is a 0 plus 4 lambda this time minus 1 into this is 3 into 2 is 6 plus 4 and plus this is a 2 lambda minus 0. That's all. This is a 4 lambda plus 2 lambda, that is 6 lambda is equal to 10. So lambda is a 5 by 3. I think that's the answer. Lambda should be 5 by 3, then only these three vectors will be the coplanar. If anyone have a doubt here, yes, you can ask.
No, sir.
No doubt. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . .
Sir, could you go back for 1 minute?
Pardon?
Could you go back for 1 minute? I couldn't pick.
Yes, I will wait. No issue. Just I will show the next question because few of them can do it. Okay. So if you complete it, tell me so that we can start this. If you done the previous question.
Yes, sir.
Yes, sir.
Okay, good. Yes, so now I want anyone how to prove this. Just you can raise your hand also. You can raise your
So we
hand.
can,
Yes, 138. Yeah. Hmm.
so we can apply one property like out here. It's like a box of B plus C, C plus A, and A plus B.
Hmm.
So we can consider B plus C, C plus A, and A plus B as LMN. And so the box of element will be a box of ABC into then we can write 0 1 1, then again we can write 1 0 1 like that, and then we'll
No,
get
no,
it.
no, not correct, not correct, not correct. Because it is not like we have the vectors I, J, K there or A, B, C are the general vectors were given here. Yes, the first thing that you identified that is correct, it is a box product. That is the only hint and that gives you the answer here. So we are given a left hand side of this is that is LHS, I will say, as a box product of B plus C, C plus A and A plus B. This is mainly the hint that you have. Yes, now anyone guess here what should be done or which property we should apply to get 2 times the box
So
product of A?
distributive
Yes,
property,
distributive
distributive
property,
property.
and that's the correct
Determinant.
answer. Just we have to apply the distributive property one by one to each term. You can apply it one step also, but I will do it one by one. So I will apply the box product, distributive property to the first term here. So I'll say it is a B, C plus A plus B plus. Now that is the B is there, so it is a C now plus C, C plus A plus B. So just to apply the distributive property to this first term, and it is getting as a sum of the two box products now. So exactly same thing we can do it for the remaining now. So we can apply the distributive property to this term, and we get box product of B, C, A plus B plus B, A plus B. So we apply, just we applied here the distributive property to the first box product, and this box product is converted as a sum of the two there again. Same thing we can do it. Now we apply the box product, this distributive property to the middle term of the second, and I will write the here as C, C, A plus B plus that C, A plus B. What should be the next step? Yes. So one of the box product goes to the 0. This box product value
Yes,
is a
sir.
0 there. Okay. So the box product value, because one of the vector repeats there as C, A plus B. When two vectors are identical in the box product, that value of a box product is a 0 there. Now the similar thing that we can do it, we can apply the distributive property to the first term, and we can reach here as a B, C, A plus B, C, B. So this is distributive for the first. Now we'll apply here the distributive property to this term, and we get BAA plus BAB. Okay. In the same way, there is one more now, so I can write for that this one, A plus B plus CAA plus CAB. Which of the box product goes to the zeros now?
Sir, all the middle terms.
Second, third, fourth, and fifth.
Second, yes, second value is a 0. The
Third,
BA
fourth.
is also 0.
Third,
This is
fourth, and
also
fifth.
Fourth,
0. And this is
fifth.
also 0. Yes.
First
So
and last are same, so
first
it
and
will be 2
last are,
times.
yes, if there is a cyclic change in ABC, they are the same. So first can be written as ABC, and last also can be written as ABC again, because cyclic change in ABC. So it is a 2 times box product ABC, and that is nothing but that is RHS of the given expression. Okay, so just two properties we used. One is a distributive property, and the second is cyclic change in ABC. The value of a box product remains same there. Any doubt?
No, sir.
So tell me if you
No,
finished
sir.
so that we can move to the next then.
Yes, sir. Finished.
All of you completed?
Yes, sir.
Okay.
Yes, sir.
So next question. Yes, anyone? What should be the hint?
Sir,
Vector triple
inside the
product.
bracket, we can do vector triple product. No, we can consider any one as another constant, and then we can do it like C cross A. We can take it as D, so it'll
Okay.
become B cross C cross D. So it'll be B dot D into C minus C dot D into
Okay,
B.
good,
So
good. So inner bracket, the main hint is that inner bracket B cross C cross C cross A considered as quadruple product or triple product, and you can use that formula. So let me start with LHS. So if the question is asked this way also, you have to write in this form. So you can start with left hand side, that is LHS here, and we can write A cross B dot B cross C cross A. And now here we have to apply that formula. So there are multiple ways. So yes, if you remember that 123 formula, so you can consider this as 1, this as a 2, and this as 3. 123, and we know what is the formula. 123 is 132 minus 231. Okay, that is our formula that we see. So this will become that A cross B as it is, and now this is 1 3, 1 with 3. Am I correct, or
It will be 1, 2, 3.
it is 1 2 3 last one, na?
Yes, sir.
Okay, because I taken this as 1. So if you consider, if you want to use 132 minus 231, here you have to take 1 2 and this entire part as a 3 there. Okay, so you should use a correct formula. Both way you will get the same answer. So 132 minus 123 only I am using right now. So you can use any of that. So this is the box of B C 1 3, that is BCA, into, now into the 2 is left, that is a C, minus the box of BCC into A. And obviously this one of the box BCC goes to the 0. The box of BCC is 0 there. And what we left now? Now here is one most important thing now. Okay, this is one of the most important thing to understand how we are writing now. What is this BCA? The box product is, what is the resultant quantity? This quantity is a scalar. This is just a number. Suppose this number is a 10. So this 10 number goes outside, and this, whatever the dot, this dot is there. Here is a dot between these two brackets. So this is a vector. A cross B is a vector. C is also vector. So obviously this dot goes between the vectors only. This dot goes between the vectors and scalar will come out. So I can write that box of BCA, that scalar constant outside, and we can write it as A cross B, this A cross B dot C. So dot product goes between the vectors and scalar will, constants comes outside the product, dot or cross. So what is this? A cross B dot C. That is again a box ABC. Okay, this is actually BCA is a box ABC because cyclic change, and this is into a box ABC there. And what is the answer then? It is a box ABC bracket square, and that is our RHS. Okay, so this is RHS. So those who are interested, those who are not interested to remember the new formula, that is 132 minus 123, they can do it with, take this as 1, as a 2, and this entire bracket as 3, and then you can use the same formula 132 minus 231, and you will get the same answer there. Okay, so choice is yours. You can go by any of the way. Any doubt? So this one is asked last in 2012. So I think after 2015, these questions never asked. So before 2015 only these questions are coming, but still it is a part of our syllabus. So we can't say at any stage some examiner, if you want to ask, you should know how to do this. Any doubt?
No, sir.
No doubt. All you completed? Are you completed, all of you?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
I'll check, is there any example left? Yes, there's still one more example. Show that A cross of A cross B is A square into B cross A. So obviously there are, which formula we should use?
Vector
So
triple product.
182
Vector
minus
triple product only. You
132.
should
123.
focus on the square bracket only and apply the vector triple product, and then you can get the required answer. LHS A cross B, and this is again that 1 2 3. So what is the formula? 132 minus
1, 2, 3.
2, 3, 1.
132 minus 123
123.
or
123.
okay 1 2 3. Okay,
Sir,
yes. Okay, so let me check. If you are not getting the answer, then this formula will be wrong then. Okay, there is another way to rewrite in the exam because you have the answer with you. Okay. So 1 3 1 3 is A dot B into A minus 1 2, that is A dot A dot A into B. So this is by definition of a vector triple product. Vector triple A dot B into A minus A dot A into B. What is the value of A dot A?
A square.
Okay, very good. Generally, I get the answer from the students as A dot A is a 0. So A cross A is a 0. A dot A is never 0. So that is a square. Okay, this is the a square. Now, what about this a dot b and a dot a? What these quantities? These quantities are a
Scalar.
they are
Scalar.
scalar, and
Scalar.
here is a cross. So this
Yes,
cross
sir.
goes between the vector and the scalar will come out. Now, if you take a cross inside, what will happen? This a dot b is a scalar number, remain as it is. A dot b is a scalar number, and this cross goes between the vectors, so we get a cross a minus. Again, a dot a is a square, that is a scalar, and this cross goes between the vector, this one, a cross b. Clear? What is the value of a cross a?
0.
Just we see that is a 0. This a cross a is a 0. And what about the minus sign? Minus sign, if you merge inside the bracket, the order of that cross product will change, because cross product a cross b is equal to minus of b cross a, and we got as RHS. That's the end of the proof.
Excuse me, sir.
Yes.
Sir, like we can take like A cross B as a C, so it will become like full A cross C. So then we can do
Okay.
like that also, no?
Okay, that way also we can proceed. You are correct. So choice is your. You can apply how you look to the problem. That is the important. And if you have some, okay, as you look that a cross b as a new vector as a c there, and you apply there, then also you get the same answer. Correct. So are you completed, all of you?
Yes, sir.
Yes, sir.
Yes, sir.
One second.
Oh, just I erased. But okay, okay, I will wait it. I think that was the last question. Did I see? Yes, that was the last question.